Hello, this is Paul. In this lecture, we are going to find the limit of a convergent sequence. Use different methods. The first, we use the property of the limit law of a sequence. And this property is similar to the laws for functions we learned in Calculus 1 before. And for example, here is the sum rule, right? This is the difference rule. The sum rule, we call it the difference rule. The scalar multiple, the scalar multiple rule. This is the constant, right? And this is the product rule. This is the quotient rule. Of course, the denominator cannot be equal 0. And this is the continuity of the function x with the piece power, right? And so we don't need to prove this. We did it in Calculus 1 before. And we use this to do, let me see, 2 examples. Can we see? So the first example, if we have a sequence, okay, the general term is here. So how to is already tell us this sequence is convergent. How to find the limit? We just use the rule. So we just see. Look at this. So I directly put the limit of that. Can you see? This is easy, right? In Calculus 1, at the beginning of limits of Calculus 1, we learned how to find the limit when n approach to infinity divided by n both numerator and denominator, right? Okay, so up here, so this is easy to get. So the limit n approach to infinity. So here is 3n over 1 plus 6n. We can do this. Okay, divided by n. Okay, divided by n both numerator and the denominator. See what do we get? We will get here is 3, and here is 1 out of n, right? So here is 6, just divided by n, and then we use the limit law of the sequence. We just see, we just solve. And this limit can go to the bottom, right? This is the limit of a quotient, and then the limit of the sum rule. Okay, definitely this limit can go to here. 1 out of n. When n goes to infinity, that's 0. Means use the property. This equals what? Equals 3 over 0 plus 6. Okay, and here we call that the limit law, right, of a sequence. So we just learn, and do calculation, of course, equals how many? 1 out of 2. So did the results. Okay, this is not difficult. So we already learned this before. Then we look at this an, how to find the limits. So they are similar, but this time we cannot divide it by n, both numerator and denominator, divided by the highest term, okay, which is x squared, right? Okay, divided by x squared. So we're going to see, so we have the limit m approach infinity, and 3 plus 5n squared n plus n squared. We can do this. We can divide it by n squared, both numerator and denominator. See what do we get? So here goes to 3 over n squared plus this we go to 5. Divided by n squared, we have 1 out of n left. Divided by n squared, we have 1. Okay, and then we use the limit law of sequence again. The limit law of sequence, you can see the limit law of sequence. Okay, we just did, and then we use the quotient rule first, and then the sum rule. Okay, and then this goes to the limit. This goes to the limit of 0, right? And then what do we have? We don't need the limit, and then is what? The first is 0, and then is 5. This is 0 again, and then plus 1. See what do we get? And we do get a 5. Okay, so these are 2 examples for the property. So look at the property, is not difficult, right? This looks nothing new. We learned it from Calculus 1. Look at the second type. The second type we do this, okay. Or at the first we need to look at the results. Okay, we need to use these results. Okay, and these results are famous. And we just say R is a variable. R is to the nth power. R is a constant number. R is to the variable n. N approaching infinity. So look at this. This sequence of the last topic we did, right? Okay, this sequence convergence only and if and only if R is between -1 and 1, including 1. Do you remember that result? Okay, so here, if R between -1 and 1 does not include open interval, definitely goes to 0, because it gets smaller and smaller, go to 0, right? If R equals 1, so that's 1, 1, 1 constant. The limit of the constant is itself. So here is 1. And another, this is the convergence case. Of course, for all other cases are divergent. For example, if R greater than 1, what do we have? Okay, it's the divergent to positive infinity. Okay, another I did not write here. If R less than -1, okay, it's oscillate. Remember, it's oscillate like a wave. Sometimes positive, sometimes negative. So it does not exist. It's not because divergent to infinity, not divergent to negative infinity. Okay, so we don't need that. So let's look at this example. So what is the limit? That is related to the results I just showed you. Yes, but how? We'll look at it here. So we have two base, right? The base 4, the base 9. We need to merge the base into one. How to put it together? So we do this. Or first we look at it. This is R greater than 1, infinity over infinity, right? It's an indeterminable case. So how to do? We need to modify a little. So I'm going to show you how to modify. It's just this. I copy that to here. That the limit m approaching infinity, okay, is 4 raised to the nth power 1 plus 9 raised to the nth power. How to find this? Infinity over infinity, but we can divide it. So divided by the bigger one, okay, 9 raised to the nth power divided by 9 raised to the nth power, both numerator and denominator. So we try to merge them together. Can you see? After we merge, what do we get? So this divided by this, so it goes to 4 over 9 raised to the nth power. Okay, so this one goes to 1 over 9 raised to the nth power. You can see this is R is less than 1. Okay, so that's good. Plus 1. And we go to here now is easy. Why? Because we know from the results this goes to 0, this goes to 0. Okay, so that equals 0, 0 plus 1. Okay, so how do we get this? This is from the result 1. We just get result 1. Therefore, the result is how many? Is 0, right? Okay, did the result. And did the second type. So we're going to look at one more type. Can we see this? Okay, so another type we have to use this squeezy theory. In Calculus 1 we learned, right? Squeezy theory is famous. Okay, so in sequence is this way. If we have 3 sequence, the Bn is the middle one. Bn is squeezed by An and Cn. If An and the Cn had the same limit, that means the left approach to L, the right approach to L again. Of course, in the middle, squeezed. Definitely we need the limit equals L, right? Okay, so I don't need to prove. So how do you use that? Can we see one example? Okay, all we need to do is squeeze this An, right? How to squeeze? Okay, I wrote a little bit different way. I wrote this. So this negative power goes to the bottom. I wrote cosine n times pi over 2 raised to the nth power. This is the same, right? This is the An. Okay, we look at this. Cosine is between -1 and 1. That's all we need to squeeze. So this is greater than -1, right? So -1 over 2 raised to the 10th power, less than or equal to 1 over 2 raised to the 10th power. Okay, this is easy to do because the cosine is squeezed by -1 and 1. So this is the squeeze. And now what do we need to do? Look at the left limit. The left limit equals 0, right? Because the bottom is infinity. That's 0. This is 0 too. Okay, that's all we need because both the limit L is 0. So the middle at the limit is 0. So now what do we need is because we know the limit of the left. The left is -1 over 2 raised to the nth power equals the limit of the right and equals 0. See, both equal 0, the middle is 0. Therefore, we have this. We have our limit m approaching infinity. An, okay, if I wrote here, is cosine m pi over 2 raised to the nth also equals 0, right? L equals 0 in this case. If we wrote a little bit detail, is by the squeeze theorem. Okay, so that's easy to get. If you squeeze the function, that's very easy to get, right? Okay, this is one type. Let's look at another type. Okay, so look at this. I draw a graph for you here. Can you see the graph? Okay. This graph tells us we have a theorem. We don't need to exactly need to prove. And exactly the last topic we used this. Can we see we have a function y equals f, and from the function we pick the discrete point. So when x equals 1, we pick n, right? N equals 1, which means this height f at 1 is a1, this is a2, this is a3 if you like, this is a1, a2, a3, a4, a5. Okay, all the a means what? An, the sequence picked from the function. See, if one look at it, the sequence has a limit only depends if the function has a limit. So this graph shows us the function will approach to L, right? Which means the limit of f when x approaches infinity equals L. The limit of f is L. Therefore, okay, the sequence has the same limit of L. Okay. Sometimes this is very useful. For example, here, can we look at it? This sequence, okay, and the other method that you can try, you cannot figure out, okay, and this is convergent. Definitely, this is convergent, and exactly we can find the limit of this sequence. But how? Try to use this theory. Okay. So first, this an is came from a function. Which function? Should be like this. Came from a function. Can you see a function? We can say a function is this. Ln at x over x. Can you see? Okay. This is the function, and from the function you pick a discrete point, and which is the sequence. And then now, all we need to do is look at the limit of the function, right? We need to know the limit has a function. The function has a limit. Therefore, the sequence has the same limit. So, I was going to do how to do this. This is not difficult. In Calc 1 you did. So, for the limit x approaching infinity, this function is ln x over x. Can you see this? This is infinity over infinity. You need to do what? L'Hopital's rule, right? Okay. L'Hopital's rule we're going to use. Take a derivative to there, take a derivative to the bottom, which means we have the limit x approaching infinity. The bottom goes to 1, and here goes to 1 out of x. Okay, so this now is easy to look at. So the top goes to 0, right? 0 over 1 is 0. You know, this we call it the L'Hopital's rule, right? And the L'Hopital's rule, this is very famous in Calc 1. Okay, Now what do we have from the theory? Okay, the function has limit 0, therefore the sequence has the same limit, also 0. Now directly get the results. So the limit of our sequence is n approaching infinity ln at n over n is the same limit equals 0, right? Okay, so this is by our theorem before, the theorem 1, if I say. Okay, this is one case. Let me look at another case. Okay, so look at this. And can we look at the sequence? The sequence is oscillate. Oscillate, however, is the approach to a fixed number. Okay, sometimes it's positive, sometimes it's negative, right? We call it oscillate. However, here we have a theorem. Okay, and if the absolute value of the sequence goes to 0, and the sequence should be 0, right? No matter is how, and at least we see n gets smaller, smaller. No matter is positive small or negative small, and finally we approach 0, right? So the sequence should have the limit 0. Okay. Can we see this? So all we need to do is look at the absolute value. Can we see the absolute value? Of course, it's easy to look at the absolute value. The limit m approaching infinity. Absolute value of this over m. Okay, absolute value is what? It's easy to find, very easy. Is how many? 1 out of n, right? So n goes to infinity, 1 out of n goes to 0. See, super easy to get the absolute value. Therefore, this theorem tells us, therefore we have the results directly. Therefore, our sequence, which means an, right? An is -1 over to the nth power of n. See, this one is also has the same limit of 0. Okay, by the theorem 2, if we say by theorem 2, okay, that's one example. Okay, so the one case, the last case. We will look at the last case. Okay, look, it's complicated this time. However, we did this before, right? Okay, the last topic we did. This is a convergent sequence. Convergent sequence. Why? By the monotonic sequence, right? Do you remember this monotonic sequence theory? Okay. Why? Because this is bounded. Yeah, this is bounded above, and then it's increasing, right? If I write here, for some of you forget it, I'm going to check the last topic we did. We did all the details. So here I just summarize a little. This sequence, we simply say AM is bound above by 2, right? And this sequence AM is increasing. You can go into the last topic to find the detail of this. Therefore, what do we have? Okay, and the sequence is bounded and increasing, monotonic. We have a monotonic sequence theory, right? Let me see. So we know an, this sequence converges. Of course, it's by monotonic sequence theory. Do you remember this? This is a famous theory. Okay, therefore we can what? We can set up the limit is L is a variable, and then we make equation to solve that. So we can do this. I'm going to let the limit m approaching infinity an equals L, and this is a variable. I try to make equation. Okay, so we have to make equation. So from the sequence, so where is the, we can find this equation. So this kind of relationship, an equals square root of 2 times am minus 1. Can you see? A2 equals square root of 2 times a1, right? A3 is square root of 2. This total term is A2. Okay, it's not difficult to find this. If somehow you want to prove, you can use the mathematical induction, right, to prove this is correct. Of course, we have a name. This we call the recurrence relation, right? This we call the recurrence relation of the sequence. And then now, so it's easy. We can take a limit to the left, take a limit to the right of this equation. So the limit go to the left, am equals the limit of the right. The right it is sorry, this is not this is a 2. Okay. 2 am minus 1, and the limits go inside because of what? Because the continuity. Okay, so it's square root of this 2 times limit m approach infinity am minus 1. And you see, because we already set up the limit equals L, so how do you think this also has the L, alright, the limit? Therefore we have equation. Therefore we set up equation. The left is L, the right is square root of 2 times L. Okay, and the square both sides, very easy to solve. What do we get? We get L equals 2, right? This is the results. See, this is a famous sequence, so we can get it. The limit is 2. Just that's all. Thank you.